Welcome everybody to lecture 11 of our robot learning course. Very excited today to talk about what I think is one of the frontiers nowadays in robot learning. So we will be talking about embodied reasoning and test time scaling. So I want to start with this kind of question, right? Like over the last few lectures, we've covered how to train large models with on large data sets. We've covered VLAs and so forth. And so one of the questions you might be asking yourself is like, well, it seems like, just we can keep collecting robot teleop data and that's all we need. Like we just scale this kind of recipe from LLMs and we're good to go. And this is true. I think it's not the full story, and I want to be careful here. So I'm not saying that data doesn't matter. It absolutely does. But consider what data actually gives you, right? So it will give you like a better prior over the behaviors that you have, right? It some kind of like compresses the distribution of the demonstrations into your model weights. And so what is missing, I think, is intelligent reasoning. And what I mean by this is that essentially, we've saw like some very impressive like VLAs and so forth in the previous lectures. And even if we succeed in building a robot capable of many tasks, this isn't going to be very useful if it's not also able to reason intelligently. So for pretty much all the models we've looked at so far in the course, like even the most capable VLA or something, if these models encounter an out-of-distribution situation, they typically don't have a mechanism to intelligently work their way out of it. Like they will kind of like fail, right? Which separates it a little bit from like the intelligence that maybe we as humans might have. And with respect to like this scaling the data angle, right? We can make an analogy looking at LLMs, right? Which are trained on magnitudes of more data than our largest VLAs nowadays. So LLMs, even after training on all of the internet, it turns out that all this data is still not enough to solve all the problems we want LLMs to solve for us, right? And for robots where data is orders of magnitude more expensive to get, it's almost certainly not going to be enough too. And so the alternative in LLMs nowadays is to train specifically for reasoning. And the key intuition here is that reasoning is compositional. It basically consists of reusable building blocks of like logic and knowledge that then you can recombine to solve novel problems with existing knowledge. This means you don't have to have seen a certain situation before if you can reason your way through it from first principles. And this is what we're going to talk about today. How, like, for robotics, we kind of want the same properties of endowing them with this intelligent reasoning abilities that allows them to generalize beyond the behaviors that they have seen in the training distribution. And as we've been formulating robotics as a multi-model sequence modeling problem, right? So consuming images, language, and action tokens, we've already been transferring many advances from LLMs and VLMs, model architectures, pre-training objectives, scaling strategies, and so forth. So the natural question is, can we also transfer some of the algorithmic improvements that have dramatically helped LLMs and VLMs to generalize, such as reasoning, right? So in today's lecture, we are basically going to ask, okay, instead of just scaling pre-training, can we make, will a robot that things harder make it act better, right? And this brings us to the first paper I want to talk about, which is embodied chain of thought reasoning. The core idea here is simple. So instead of having a policy or a VLA, in this case, map directly from like an image and an instruction to actions, we insert some intermediate reasoning steps. Given like a concrete instruction, we will ask the model to first generate some sort of a plan, like move like to the watermelon and so forth, like identify what are like the next subtasks the policy should do, and ground these also in the images. So it's kind of like chain of thought, but like applied to the physical world. Oh yeah, and here is an animation for this that kind of compares this to like the non-embodied chain of thought version. So the first question is like, where does the data to generate this reasonings come from, right? Because we can't ask a human annotator to label every trajectory in like a large robot data set, like with a plan, a subtask description, like bounding boxes, gripper positions, etc. Like that isn't really scalable. So the idea is pretty simple. As probably you can guess, it boils down to using internet scale foundation models to annotate your existing robot data set by generating semantically grounded reasonings like these bounding boxes of like the object your end effector is going to interact with next, traces of how the gripper is going to move into the future, and so forth. And now, kind of to repeat the core idea of this embodied chain of thought architecture is really to train an autoregressive vision language action model that predicts this intermediate grounded reasoning steps. So the task, the plans, the movements, and so on, before predicting the action tokens. So essentially, this means we are now forcing our model to think carefully and look carefully before acting, right? And so the action tokens get conditioned on this intermediate auxiliary reasoning tokens. Okay, what does this bias? So we, in this work, we evaluated now this VLA in really challenging out-of-distribution scenarios in the real world, like distractor objects, spatial relations, and so forth. So all kind of unseen objects and unseen instructions and scenarios. So everything was kind of out of distribution. And here, I think this result is like pretty significant. So we found out that applying this embodied chain of thought technique brought a 30% performance boost over OpenVLA, which is the same model but without the reasoning. And it also outperformed a much larger model from Google, RT2X, which is a 55 billion parameter VLA, compared to our model here, which just had 7B. So the key message here is really that without collecting any additional robot data, for the same amount of robot teleop data you already have collected, you can improve your model's generalization capabilities by around 30% by applying this embodied reasoning technique. And as a side benefit beyond generalization performance, it also gives you better interpretability and interactiveness. Because now, because these reasoning steps are like human readable, you can see like where it's predicting the bounding boxes and so forth. At test time, you can also see like if the robot is predicting a wrong plan and edit this reasoning chains online And because the action tokens are conditioned on this intermediate reasoning tokens, it will naturally kind of self-correct itself, like if a human intervenes and like edits the predicted reasoning chains online during inference. So that's pretty cool because it makes the whole model also more interpretable. Like if it fails, you can see like why it failed and so forth. And one of the coolest experiments, I think, from this paper is that it actually also generalizes the reasonings to unseen robots. So here in this work, the VLA model with reasoning was trained only on reasonings from a single data set, the WidowX kind of like this cheap like black end effector robots that you saw. And then we applied this to different data sets from the OpenX embodiment, different data sets as you can see here, and ask it to produce these reasonings. And as you can see, despite like the model looking at a completely novel robot, a completely different camera, everything is new, it still produces very plausible reasoning chains. And why is this? Because a lot of the tasks, reasoning tasks, are actually quite similar to the VLM pre-training tasks, and therefore the VLM already kind of has this like world model. And so this embodied chain of thought is kind of trying to it's kind of unlocking like the reasoning capabilities that are already inside the VLM thanks to its pre-training. And so yeah, this kind of suggests that embodied chain of thought like could be a principal way to transfer reasoning across different embodiments without having to collect demonstrations and annotate them for every new like robot morphology that you might have. And yeah, so to summarize, the core contribution here is to establish a new way to train VLAs with embodied reasoning, showing that you can improve generalization, interpretability, and interactiveness without any additional robot data. And it's been, since then, kind of adopted both in academia and industry. For example, Gemini Robotics VLA incorporates this as a core component, which I think is kind of a useful signal because it suggests that the field is converging towards treating reasoning as a first-class component in the robot policies. And there are like a number of follow-up works exploring different angles to embodied reasoning, like Molmo Act, for example, that's spatial reasoning with depth tokens. Clark et al. Transferred action-free reasonings from reasonings coming from human data by decoupling the reasoning training from the action prediction so far. And so I really encourage you to check these papers out because, yeah, I think they kind of give you a good picture of like where the field is kind of like heading towards in terms of embodied reasoning. Now, there is an obvious problem with all of this. Reasoning is unfortunately slow because we are basically increasing the number of tokens generated at test time quite significantly. So OpenVLA, which is kind of the base model we were using in this work, runs like it's a 7B model, so it runs about 4 actions per second. And the embodied reasoning version of it that we developed, because it had to like produce like this full like reasoning chains at every step, runs at 4 seconds per action. So it's quite a difference. Like we managed to do some inference speed optimizations later on, but the first ever rollouts that actually Will and Michal, who were the lead authors of this work, did on the real like WidowX robots were really painful, like just to watch. Like watching them do these rollouts with like doing like one task was taking like so forever. It was like, I don't know, 1 hertz or I don't know what. It was really like, yeah, painful to watch. So the question is, like, well, as roboticists, we care about like having fast control. We want, have real-time control, and we don't want to like, also spend hours and hours watching our robot like move like kind of at a very, very slow speed, like a turtle speed. So can we get the benefits of reasoning without paying this kind of inference cost, right? And so before we jump to solutions for the inference problem, I think it's actually worth pausing and asking a more fundamental question, like why does embodied reasoning work at all, right? Because, and I want to be like a bit careful here because I think like there's kind of a tendency in the field where, especially in machine learning, where we see that something works, right? Like, oh, like 30% more generalization performance, whatever. We get excited about it and then we move on to the next thing. But if we don't understand like why it works, we can't really know like when it will fail, and we can't know how to improve it. So we can't build on this in a principled way. So in the same scientific rigor we apply when experiments fail, I believe we should also apply when things succeed. And so in the next few slides, which are adapted from Will, I'll try to shed some light around like some different hypotheses that sound plausible for why this could be working. And so the first hypothesis is better representation learning. The idea is that the reasoning traces somehow supply additional knowledge that shape the model's internal representations, like saying okay, like indicating somehow like the particular object's location is relevant, or a specific movement for this scenario matters, and so forth. Like basically forcing the the model to build richer, more semantically grounded representations for the scenes. And if this turns out to be the primary explanation, then what actually matters is the supervision signal itself from the reasoning during the training, not necessarily generating the reasonings at test time, right? So the model's representations would already be attending to the right features, even if we skipped the generation of the reasonings at test time, right? And so if this hypothesis would be kind of true, then the consequence would be really appealing in that we could train with reasoning for better representation, but deployed it without to recover the the low latency and the higher frequencies. Another hypothesis that sounds also plausible could be that this embodied reasoning provides an improved learning curriculum. So the intuition here is that predicting continuous robot actions is extremely out of distribution for a VLM that's been pre-trained on like image, visual question answering, and so forth, right? So directly taking a VLM and then fine-tuning it, end-to-end to produce continuous robot actions is really hard. It's like, wow, it's completely something different to what the pre-training has been doing. And so it could be that embodied reasoning provides some sort of implicit curriculum, right? So the model can first learn kind of more intermediate, more simple tasks like mapping movement descriptions to actions, and then work its way up to the full prediction problem from like pixels to actions, right? And so the practical implications of this would be, if this hypothesis is true, that then we could use reasoning just purely as a training scaffold by providing, let's say, reasoning examples in context during training, but without any loss on them, and then remove it at inference time, getting kind of the generalization benefits again, but without the inference cost. And then the third hypothesis is increased policy expressivity. The idea here is that just simply having more tokens in context even if they might be semantically meaningless, increases the expressive capacity of the transformer when predicting actions. And actually, this is a very, very plausible hypothesis because it's been very well documented in like LLM studies. So I put here two references that also study this, that show that LLMs or transformers can use like intermediate tokens as a scratch space for hidden computation, improving performance even when those tokens carry no semantic meaning. And so this really raises a very important question in the sense of, like, for embodied reasoning, how much of the benefit is coming from the semantic content of the reasoning, and how much is it just coming from the extra compute budget that the additional tokens provide. Because if it's mostly the latter, then the specific grounding of the reasoning matters less than we might think, and we could get the same benefits much more cheaply instead of like using foundation models to try to have very nice labels, right? And so in this work, ETH Light, these three hypotheses are empirically tested on the Libero 90 benchmark by isolating kind of each mechanism individually. And here are the results. So reasoning pre-training and reasoning dropout, which I will cover in a bit, and both remove reasoning and test time perform almost as good as the full original embodied chain of thought. The reasoning scaffolding, where the reasoning is provided as an input context, but without loss, also does quite well. And the thinking tokens experiment with like the kind of like null tokens, although better than the standard VLA, doesn't close the. Oh, it's not better. Yeah, it's a bit worse than the standard VLA, so it doesn't really help. So. Yeah. So I will briefly explain kind of the reasoning pre-training and dropout that worked so well. It's quite simple to understand. So the reasoning pre-training is pretty straightforward. So this means like you have two training stages. In the first one, you just take your VLM and fine-tune it to only predict the reasonings. So you don't have any action loss or no action prediction. Once you have finished training this model, you start, you take that model, and then you fine-tune it to predict continuous robot actions. But without the predicting the reasonings. So you're really transferring just the representations learned in the first stage, right? And then in the second one, you don't predict the reasonings at all, just predict the actions, so that you don't have the cost at inference of predicting the full reasonings, right? So you decouple both. And then the reasoning dropout is a single joint training stage, like the original embodied chain of thought, where you jointly train the model to both predict the reasonings and actions. But what you do here is that with some probability now, during the training, you drop out the reasonings so that the model learns to also produce the action tokens not conditioned on the reasonings. So this allows you now at test time to choose if you want to generate the reasonings before predicting the action tokens, or if you want to turn it off. So now it gives you this option to turn it on and off the reasonings. And here you can see the same results for real-world experiments with the real robot. And you can see on the left plot that basically like the original embodied chain of thought. So during inference, generating the full reasonings gives you the most performance in terms of generalization success rate, but at the cost of lower inference frequency. And then these two variants, the reasoning pre-training and reasoning dropout, are slightly worse in terms of generalization performance, but basically give you the same frequency as the standard VLA. So which of these two should you use? It depends really on your constraints. So as I said, the original one is probably slowest for most real-time settings. Reasoning pre-training is especially good if your reasoning and action data are not paired. So if you have like other sources of data that are not robot data, where you want to transfer reasonings from, like from simulation or human data and so forth, then that's the way to go. And reasoning dropout is the most flexible because you can turn on and off with a single model the reasonings depending on your latency budget. All right. So everything we've covered so far has used a fixed compute budget at test time. And the natural follow-up question is, what if we let the model think longer on harder problems? What if more compute at inference time translates to better decisions? Because like in the kind of original embodied chain of thought, like there was kind of a fixed number of reasonings that the model was trained on, and then it was like, okay, these are 7 different like reasoning steps, so I will always produce all 7, right? And so the idea here is test time compute scaling, right? And this is kind of the second half of the lecture. So if we like, can we improve the performance if we like think harder at test time? And you probably might be wondering, okay, isn't just that planning, right? It sounds like that's kind of what we know as planning from like 50 years ago with like A-star, Monte Carlo tree search, and so forth. And here I've kind of put like a small comparison where you can see how this compares like from where you start like kind of from really hand-specified kind of domains to kind of doing this test time compute scaling in implicit like in like with neural networks in the weights, right? So the scope really goes from structure, discrete domains, all the way to open-ended tasks like language and coding. So we are kind of each step kind of trades off explicit structure for generality. The canonical example of test time compute scaling is AlphaGo. If you remember from a few years ago, right? And here is a very interesting, the very interesting performance from the Nature paper they wrote, where you can see that the raw policy network without any search sits around 3,000 ELO. And when you add the Monte Carlo tree search at test time, you jump to over 5,000 ELO points, well into superhuman territory. Now, the rule of thumb is quite striking in that typically, there is this rule of thumb that gaining around 120 points, ELO points, requires either doubling the model size or doubling the test time search budget. So they are kind of interchangeable. And so this means that in order to get from the 3,000 ELO points from the raw network performance to the 5,200 points, that would require, without the tree search, without Monte Carlo tree search, that would require making the model roughly 100,000 times larger. These numbers are maybe are a bit inflated because AlphaGo was trained by playing against earlier checkpoints of itself, so probably the real number is not that high. But still, once maybe like interesting fact about this is that as far as I know, to this day, no one has built like a model that surpasses the human performance without test time compute search. So just like by making the model bigger. So every Go like agent uses test time search. And so the takeaway from this is really that test time search like can give you a real massive benefit. Now, of course, like this has been shown in many games, in Go, in poker, and in other kind of like game settings where you have like a perfect verifier and very well-defined search space. The question is, does this hold also in language, where tasks might be more open-ended, right? And the answer is yes, but with a nuance. So in this paper from Charlie Snell, they showed that in a flops match comparison, compute optimal test time scaling beats a model that's roughly 14 times larger. And that's quite an impressive result, because it says that for the same, the paper, like this result says that for the same compute budget, you're often better training a smaller model and letting it think longer at inference than training a larger model. How they did this here, the mechanism they used is that they kind of supervise the model's own fail attempts with the learned verifier. So the model learned to produce better answers given the previous wrong ones. And then the verifier picked the best one. And then the second, like at test time, they generated multiple answers and selected the best one again with the verifier. So really, like the thinking here is a little bit kind of like a search over the model's own output distribution guided by a reward signal. But here in this plot from the paper, I think is very interesting in that the picture flips on harder questions. So like you can see, like the green are easy questions, the blue are medium questions, and the orange are hard questions. And for hard questions, in some cases, you can lose up to 33.7% versus just pre-training a bigger model. And the intuition here is actually that test time compute amplifies, in essence, what the model already knows. So if the right answer isn't anywhere in the model's own distribution, no amount of search will help you recover it. So we've seen empirically that test time compute helps, but as I said before, it's also like kind of good to try to understand why. I also recommend checking out this paper from Lee et al. That gives a theoretical, like a nice theoretical answer. The result here says that for any problem solvable in T computational steps, it can be solved by a constant-sized transformer generating OT reasoning tokens. So the intuition here is that each forward pass through a transformer has a fixed computational depth bounded by the number of layers. And so a single forward pass can only execute a constant number of sequential steps. But by generating intermediate tokens autoregressively, the model can basically unroll additional computation at test time, right? As we've seen before. And so without the reasoning tokens, solving a problem that requires T serial steps, right, sequential steps, would need a model that's much larger. But with the reasoning tokens, a constant size model can solve it by just thinking longer. And so this is the formal kind of counterpart to what we saw earlier with the, what was it? Third hypothesis with the thinking tokens. So reasoning tokens help, but maybe like a bit of history. Where does the idea actually come from in practice? And the original chain of thought paper is very beautiful because it's very simple. Here, instead of asking, they showed that instead of asking the model to directly output an answer, that if you show it a few examples where the reasoning steps are written out explicitly by, let's say, a human, then the model learns how to do the same for new cases. But maybe one thing that is interesting from this paper is that there is a catch, and that's that this chain of thought prompting doesn't work well with small base models. And so this is kind of the figure from the paper where they show this kind of the scaling laws for the chain of thought prompting. And so you can see that for small models, it actually hurts performance, and because it doesn't kind of understand what's going on, and somewhere around the 100 billion marks, it suddenly breaks free and surpasses sometimes even the best prior supervised method. So the takeaway here is that reasoning emerges, and it requires a base model that's kind of good enough, large and capable. Nowadays, you can also distill it into smaller models, but in general, you need a strong base model for the reasoning to emerge. And so the original formulation is just really few-shot in-context learning. You manually write out some examples with reasoning traces, prepare them to the prompt, and ask it to generalize to a new case, right? And while this works, it of course has some limitations in that it's going to be prompt sensitive and brittle, depending on how what examples you put in the prompt, you will get different results. It might be even dramatically different results. And you will need a human to, or some manual labor to select and put those examples in the context. So and so it will probably not generalize outside the specific examples or domain that you provide. So the question becomes, can we train the model to reason rather than just trying to elicit the reasoning with human prompts, right? That's kind of the next question the community also looked at. And this slide shows how training for reasoning intrinsically looks like in practice. So this is from the DeepSeek paper. And so here you can see in comparison on the top part, the single chain of thought, this is kind of the clean, structured chain of thought prompt that GPT-4o will give you, for example. That is kind of following some prompted template. And then on the bottom part, the green part, this is kind of the DeepSeek kind of model, the R1, which is very different. And you can see if you can read the thinking process, it it second guesses itself. It tries to consider alternative interpretations. It even wonders about leap years. So, yeah, it's very interesting, very fascinating to see the models thinking process, how it's thinking, and it might be also a bit messy, the thinking process, but that's kind of the point that this is a model that's learned to reason through reinforcement learning on verifiable outcomes, and not one that follows a human written example, right? So also its own thinking process might not necessarily be the same thinking process that a human might do. So how do you actually train a model to reason? So the answer is reinforcement learning. Nowadays, GRPO is very popular for this. And you might recognize the algorithm because it's very closely related to PPO, which we covered a few weeks ago, if you remember. And one of the key challenges when applying PPO to language models is that the critic, so the value function, is quite expensive and difficult to train because you need like a separate network to estimate the expected returns for every possible token sequence. So it's like quite messy. And so GRPO, which is group relative policy optimization, simplifies this by removing the need for a learned value function. So instead of a critic estimating the expected returns, what this algorithm does is that you sample now a group of rollouts for one particular question, and then you compute the advantages relative to the group. So this means that each advantage is just its reward minus the group mean, divided by the group's standard deviation. And so this means that the model learns by comparing its own outputs against each other. And if you also look at the objective here, you will recognize many terms from the PPO algorithm we covered. The key thing here is what is missing from the GRPO algorithm. So there are no human labels, there are no reward models, and there are no value functions. So here, by just using binary verifiable answers, for example, for math, the reasoning emerges because the only way to consistently get a higher reward or to consistently get the right answer is to learn to think carefully about the problem. Now, an interesting question is also, why didn't this work before? Because people have been working on reinforcement learning with large language models for years. And as I already hinted before, the answer that's kind of accepted, I think, more or less by the community nowadays is that you need a base model that is strong enough to produce sometimes correct answers to hard problems. So this means that if your base model is too weak to ever produce a correct rollout, then there is really nothing to reinforce. And so what changed in modern LLMs is that they finally kind of, in the last, I don't know, like 1.5 years or so, they crossed the capability where they can occasionally solve hard problems on their own. And then once that happens, like RL can essentially take over and systematically amplify that capability. This is one of the more interesting plots, I think, from the DeepSeek paper, because here you can see like how the reasoning is emerging during the training. Like here you can see like how it's discovering this reasoning behavior purely from this binary correctness reward. So for this model, like nobody like tells us to say the words like wait, and nobody like really like labeled these are like good reasoning traces or these are bad reasoning traces. what you can see here is that until during the first training stages, until like the 6,000 steps, the model never says wait, right? So it never like says this word, and then it's just trying to get like the answers right. And then once, at some point, it discovers that stopping to reconsider improves its reward, and the frequency of like reflective language, like oh, like let's think this again and so on, jumps dramatically, and so the model like finds this on its own because it has a strong enough prior to explore reasoning strategies and not just like try to answer patterns. And this means that on a weak base model, like RL never will get past like step 0, because like if there are like no good rollouts to reinforce, like you can't discover anything. And I think this is like actually one of the most compelling demonstrations of what reinforcement learning can do that supervised learning fundamentally can't, which is to discover like reasoning, for example, here strategies that nobody explicitly like specified. Okay, so we have seen that RL-based reasoning works beautifully in language and math, but as roboticists, the kind of our natural next question might be like, well, does this also transfer to vision? The answer is yes. Well, there is like many papers in the last year that do like similar things. I think, as far as I know, visual RFT is one of the first ones that showed this, and it's pretty much GRPO applied to vision tasks. But instead of like a math grader, here the verifier they use is IOU metrics, so the intersection over union between like a predicted bounding box and the ground truth. So this means that the model still reasons inside the think tags. So like the door is on the right, like near the top, and then predicts a bounding box. And the model learns through this approach that better reasoning leads to better localization, which then gets reinforced. And the key insight here is that GRPO, the GRPO framework is basically completely agnostic to like what the verifier is. As long as you have a verifiable reward, you can apply RL reasoning to it. And similar to like IOU, like there are many other like geometric metrics that in the computer vision community are being used to kind of improve the grounding of like VLMs with RL. There is, however, an important failure mode to be aware when applying GRPO, especially to like multimodal settings like vision. And that is that in kind of the vanilla setting, GRPO only rewards the final answer. So the reasoning trace is completely invisible to the verifier, right? And so in math, this is mostly fine because it's hard to get the right answers in math through wrong reasoning. But in vision tasks, hallucinated reasonings and correct answers are unfortunately not mutually exclusive. So this means that what I'm trying to say is that a model can describe a completely hallucinated visual scene in its think block and still predict the right bounding box, either by luck or by pattern matching from the image directly. And so how do we fix this hallucination problem? And so this is actually a work we did at Microsoft called Argos, that tries to address this directly by rewarding not just the final answer, but also rewarding the, the intermediate reasoning steps. So it's actually quite simple. You have you adaptively select different verifiers, like different foundation models, for example, per sample to simultaneously evaluate the final answer's accuracy during RL, as well as like spatiotemporal localization of relevant objects, both either in single images or across videos, and so the reasoning quality itself. So this means that you can essentially check if the bounding boxes are still being localized correctly, across the video and things like that, to reward that the reasoning it's generating is actually grounded in and it's correct, right? And so this way the model can no longer hallucinate its way to a correct answer, because the intermediate reasoning is kind of being rewarded and checked at every step, including this temporal grounding in videos. And so coming back now from language and vision to embodied AI and robotics, which is ultimately what we care about, what we observed in this work is that test-time reasoning gives you large gains on high-level planning tasks, like simulated kind of tasks, like Alfred and so on. On the hardest tasks, this approach can give you 3 to 4 times better performance than supervised chain of thought models, which basically means that a model that has learned to reason through reinforcement learning generalizes to hard problems in a way that a model that has merely learned to imitate reasoning traces does not. So that's kind of for high-level planning, like navigation and so forth. But there is still the continuous control, low-level problem, right? So for continuous action prediction, you still can't afford to generate full reasoning chains at every time step, right? So what we did here is to follow the embodied chain of thought light recipe of internalizing the reasonings during VLA training and then dropping them at inference time. So I think the emerging picture for robot learning is kind of this two-level architecture where you might have this RL-trained reasoning for high-level planning and task decomposition, and then maybe like an ECOT light style reasoning internalization for fast reactive control. All right, to conclude, let me leave you with the 4 ideas that I want you to take away from today. The first one is that test-time compute is a new axis that we can scale on, and that in many settings, it's actually more efficient to scale on than scaling pre-training. The second one is that for continuous control, you don't need to pay the cost of reasoning at inference time. So you can train with reasoning, internalize it, and then drop at deployment. And the representations are what matter, not necessarily the tokens at test time. The third point is that RL can make reasoning emerge, not because you tell the model to do so, but because in many cases, reasoning turns out to be the best strategy for maximizing reward. And that's like a way more powerful regime than supervised imitation learning of human thought, for example. And the fourth is that for multimodal agents, verifying the reasoning trace is just as important as verifying the answer or the outcome. If you only reward the outcomes, you might get hallucinations. And so these four ideas together, I think, define what is one of the most exciting research frontiers in AI right now and in remote learning. And the question of how to bring all of them together into a single robot policy that can reason, adapt, and improve, that's very much an open problem yet. And with this, thank you for your attention.